Hello everyone, welcome to the final session of this Introduction to Abaqus FEA Software Beginners course. Today we're gonna learn about performing dynamic explicit analysis using Abaqus. So in today's session, I have brought these 4 examples. So example number 1 will be about a spherical ball hitting a wall, as you see here. Sounds like a rhyme. Example number 2 is a spherical ball which hits a wall, but it's more like a snooker type of example where some object hits your ball and that ball then hits a wall. So again, I just fabricated that example just to show you if you have more than 2 objects, how you can simulate or how the whole thing really works. In the third case, it's a metal forming example, my favorite topic. So in this case, we want to form this kind of U-shaped component, and for that we're gonna do a finite element simulation using Abaqus Explicit by constructing this kind of setup. Last example is about a spherical ball which drops on a steel floor under gravity, and again everything is due to the acceleration due to gravity, which is falling free fall of a spherical object. And what we want to achieve at the end of the day is we want to convert those problems which are very sketchy and coming from maybe real life or ideal world to these kind of interesting simulations and generate these kind of results. Let's jump into the first problem. This problem is spherical ball which is hitting a wall. Thus, I have assumed the ball's velocity to be 100 millimeters per second, and I'm assuming that it's going to travel in a horizontal path. Generally, when you're using explicit analysis, you have to make sure that since it's a computationally intensive process, so you need to really make sure that the time duration of the whole process is as small as possible, because otherwise it's going to take a very long time. So for long-term duration processes, it may not be suitable to use explicit analysis because it can take a very long time to simulate. Okay, in this case, we are assuming everything to be elastic. So this is linear elastic. The wall, I have given the properties of the wall here. Also for the ball, I'm assuming to be rubber type material with elastic properties and density to be this. We need density in this case because it's an explicit dynamic analysis, so we need to there will be inertia terms involved, so it needs to know the density of the material. What you have to do is you have to plot, for example, stress distributions, could be von Mises, could be maximum principal stresses, and also we need to find out what sort of stresses will be generated in the wall at the contact area and in the ball. And let's start and build this model. So I will first create a part which will be a ball, and it will be a 3D object which should be deformable, and I'm going to use a solid with revolution option. What I'm going to do now is I'm going to create a half circle here and draw a line to complete the sketch, and then I will revolve it for 360 degrees to get a complete sphere. So that's what I'm doing here. I'm going to revolve it for 360 degrees and it should give me a sphere. Yep. So once I have done that, now I need to create a wall. So I will again create a 3D wall which is deformable and it should be solid, and now I will choose extrusion here. So I will create the rectangular cross section of the wall, and then I will extrude it to a depth of 500 or 200 millimeters, whichever is appropriate for me, because the depth is not given to me, so I'm just assuming on my own. So in this case, let's say I'm going to use 500 millimeters out of plane thickness. So the width of the wall is 500 millimeters. Now I have to define the material properties. Firstly, I will define the properties for the ball, and for that, since it's an explicit analysis, so I need to define the density as I told you before, and also the elastic properties. So again, this data is provided to me in the problem definition, so I'm going to use the data from there. the properties. I'm going to use the properties from the project problem specification. And so I've defined the density, and now I define the elastic properties. Very much the same as we did in the for the static problem. The only thing is here we need additional density. So now I will create sections for each of the ball and the wall, and I will assign each solid section to that specific material itself. So this is a ball section, so I will define it as and assign it to a ball material properties. And I don't need any plane strain or stress thickness because we are working in a 3D environment. And then I will do the same for the wall, and I will create a wall section which is solid homogeneous, and I will link it with wall material properties. So now I have all the sections, and now I will tell the software that this wall, for example, belongs to wall section, which I have created which has some material properties of the wall. Once I press OK, you will see the color has changed to green. This means now Abaqus knows what this ball is made up of, and I will do the same for the ball. And I will make sure that everything is correctly selected. Now I go to the next module, which is my next step, assembly, and I will assemble as I normally do in any other CAD software. So I will bring everything to the assembly module, and then I will start to assemble it. So when I do it in the default coordinate system, you will see that my ball is at the origin because I made the center of the half semicircle to be at the origin. So you see my ball is located somewhere at the corner of the wall, and what I have to do now is I have to move it to somewhere there. So I will use this translate option here, and I will give the coordinates and position it there. So again, you can work out yourself what coordinates or where you really have to move in your case based on the middle coordinate of the wall itself. And again, I'm trying to see what is the clearance between the two, because this is again what I will decide how much far apart I will need to keep the both, because the further the ball is, more computational time it will require to reach to the wall and hit the wall. Another thing is, since the default viewport is showing me the back of the wall and not the ball, so I'm trying to create a new view as a user one, and if my view is changed, I can just click on this number 1 here, and that will basically take me directly to this view where I can see the ball and the wall at the same time, rather than just rotating it all the time. Now I'm still trying to make the clearance to be something, so I'm just trying to move it. So I will move it 1 minus 1, which is negative x direction, so that I'm trying to make it to go to a total distance of 2 millimeters or so. Once I have done that, now I will go and I will start creating the explicit dynamic step, which is the main purpose of this exercise. So I will select dynamic explicit here. I'm going to run it for 1 second for the time being. This needs to be worked out based on the distance between the wall and the ball and the speed of the ball. So we will work it out later on, and I will keep everything default, and geom is on. That's the only thing I have changed, and that's pretty much it for this step. Now we'll go to the interaction module, and I have to define a solid contact. So for that, I'm going to use a general contact between the ball and the wall, and that is basically between this. So again, still I need to define the interaction properties. General contact formulation is an excellent feature in Abaqus because you doesn't have to give the surface definition unless you have a rigid surface. Here I'm using frictionless hard contact formulation for tangential and normal behavior, and I will link it with this to the general contact formulation. So Abaqus will compute the normal stiffnesses between the two contacting surfaces based on the elasticity of the two colliding or impacting objects, in this case ball and the wall. So now I'm still trying to applying the boundary condition. My wall, as you know, is fixed from the bottom, so I'm gonna do that now, and I'm gonna fix all 3 degrees of freedom at the bottom of the wall. So that's what I have done here, and then I will now apply a boundary condition on the ball. So what I will do, I will apply a velocity boundary condition on the wall, which is given to me as 100 millimeters per second, and also I will try to fix the lateral motions of the ball and also the spin of the ball or rotation of the ball. So again, I'm just fabricating this example. You can play around with these boundary conditions and everything else to make it more realistic. This is just to demonstrate how things work in Explicit. Okay, so I will start with the velocity boundary condition, hopefully. I will select the ball. Again, you have different ways of defining the boundary conditions, but in this case I'm just applying to the surfaces, but you can apply by creating a reference point, or you can also apply artificially in other ways as well. So it's an instantaneous velocity boundary condition which will move the ball towards the wall, as you can see the arrow on the top of the ball. And now I'm going to do is I'm going to restrain or constrain the ball to move in the lateral directions and also its rotations. So that's what I'm going to do now. So all the rotations, although rotation might not be that helpful, and you will get a warning, but I'm still trying it because we're going to use tet mesh for this, and tetrahedron elements don't have rotational degrees of freedom, so you might get a warning, but it's just, you can just ignore it during the solution phase. Now it's time to mesh. Again, I'm trying to select a global mesh. As I told you, this for complicated geometries, Abaqus struggles to mesh. As you see here, it's giving us an error. So it's better to mesh, divide the part into smaller sections, or you can basically use a tet mesh. So I'm gonna go easy way this time, and I'm gonna select a tet mesh option for me, because that will make my life easier. Again, you can play around with that, and I think in the previous session I have already explained to you or give you some tips on some of the meshing techniques you can use, which are shown in this window here. I'm going to select a tet mesh, and also for tet mesh I will make sure that I'm using quadratic element to avoid any volumetric locking or any other stuff which can cause errors in my model. Since it's an hyperelastic, since the Poisson's ratio is almost equal to 0.45, so I will be careful on that. And now this mesh size is very small, and you have 19,802 elements, so I'm going to increase that to reduce it so that I can solve it and my computer doesn't crash. And it's, at the end of the day, it's a demonstration, so we don't want to spend too much time in just solving the problem. I'm going to do the same for the wall. So I'm again trying to see how much I can do. I've selected a size of 10, and based on this, as you see, my element is really fine, 37,500 elements. So what I'm going to do now, I'm going to refine the meshes at the vertical and horizontal edges, and not at the out of plane thickness meshes, because I need certain number of elements in the thickness direction to have an accurate model of the ball. So that's what I'm doing here. You can see I'm just selecting the longer edges of the wall, and I will increase it to, let's say, 20, and let's see how many elements I end up with. So from 37,500 now I have 9,375 elements. Not bad, I would say. And you can see I can use my user defined view to directly go to my favorite view where I can see the ball and the wall. Now I'm still trying to see what is the total distance between the wall and the ball, because your ball has a velocity of 100 millimeters per second, and you need to find out after how much time it's going to hit the wall. So let's say if I have a distance of 2 millimeters between the wall and the ball, then it will require around 0.02 seconds to travel a distance of 2 millimeters. And so this way you can work out the step time, which I showed you at the time. At the moment it's 1 right now, but you have to work out based on this. And again, it depends on you how far you want to put your ball away from the wall or something like that. So here I'm trying to show you how you can do it. You can go to the tools query, and then you can select distance, and then it asks you to select the first point and the second point, and then it will give you the value of the distance somewhere here in the component. So you see at the moment the distance is around 6 millimeters in X direction here. So maybe it's too much, so I will try to bring it closer to it, but let's see if it works or not. So I'm going to go back to my assembly module, and I will try to reduce this distance. I'm still trying to ensure that if my distance is correct, and it's giving me 6 millimeters. Again, the problem is I'm measuring with this edge here. In principle, it should be at the center. Sometimes the surfaces are not really aligned with the Abaqus coordinate system, so You have to be careful in that. I'm not sure why it does that, but I found this issue with Abaqus CAE. In any case, now we start to bring it closer, 5 millimeters closer, so then the clearance will be around 1. So I just give the 0, 0 as a starting point, and end point is giving us 5, so it will move forward 5 millimeters towards the wall, and now the clearance should be around 1 millimeter. So I will still try to ensure that still it is away from the wall, it's not touching it right now, because then, so yeah, it looks okay. If I'm not sure, maybe it's going in or something because of the mesh, inaccuracy in the mesh, then I will give it some kind of allowance and I will move further back. So that's what I'm doing here now, and I'm going to move it further 1 millimeter back so that I will make sure that there is a gap between the wall and the ball before it impacts. But then I will not be sure what is the exact distance, because because our mesh is very coarse, so you know there are straight lines in the tetrahedron which might be intersecting with the wall due to the corners or edges. So anyways, now I have to go back based on the distance. I am assuming it to be 2 millimeters, but it could be more because of this meshing and everything. So let's see what happens. I'm going to change the time now to 4.02 seconds, which is a step time. So I will go to this step time and I will change 1 second to 4.02 seconds, which is based on the fact that the velocity is 100 and total distance is 2 millimeters, so 2 over 100 is 0.02 seconds. And let's run it. If it doesn't make contact with the wall, we can come back and we can increase this and we can again play around with that. So again, it depends on how expert you are to measure this distance between the ball and the wall, especially after the mesh, and then that will give you the overall time of step time to reach to the impact of the ball. So here I am not showing you the precision because you always have to go to the double precision and full precision in the precision tab, but so I would also recommend to do that. Since I normally use command prompt, so I write double in the command prompt and it automatically takes into account that thing. So here I have run the job now, and let's see how long it takes and what sort of issues you're going to get at the end of the day. So you see you have got some warnings. As I told you, there is some degrees of freedom warning, and it's just because of the fact that we are trying to restrain the rotational degrees of freedom of tetrahedron mesh, which might not be active, so these are already inactive or in the element formulation of tetrahedrons. So again, you see it's much quicker. It has to run up to 0.02, so its time increment size based on the element sizes, elasticity and density is around 3.268 exponent minus 6 seconds, and we are reaching to the 0.02 now. And once it's finished, we go back to the visualization and we can see what sort of results we have got and if the ball has really made an impact with the wall or not. So again, I will change the view and I will run the simulation, but you can see the stresses are very low and the ball has not really made any impact with the wall yet at the end of the simulation. So maybe I need to go back and I need to increase the increment time, or I need to decrease the distance between the two. So easier for me for such a small simulation which is not taking that long is just to increase the step time, because it will increase few minutes and then it will be finished. But in reality, if it's a very long job, big job, and you are requiring a lot of time, then it's better to decrease the distance between the two objects. Okay, so now I'm changing it to 0.1, and once I have done that, I will go and I will run. And this time obviously it's going to take a long time, so I'm going to press monitor. Let's see, and I can see the status file, what's happening in the job. It gives you the real-time update on the job, and you can also see the same here, but it's taking a long time, as you see. So I will just increase the speed of the video. So this is not real time right now, it's around 4 times the speed, but I speed it up and you can see it's going down. It's already left 90 seconds. CPU time, it was too much for me, so I just said okay, let's go and see what's happening now. So once it's finished, you can see, then we can play around and we can see what is happening to your job. and you can see that the ball has really made an impact with the wall now, and you can see stress concentration in the wall and then stress waves traveling in the wall. So everything is working fine though, but the stresses are still very low, which is 192. This example is about a spherical ball which is hit by a rectangular object in this case, and then it basically hits the wall, and we want to see what sort of stresses are generated in this impacting object, the spherical ball, and the wall in the contact areas, and we want to see if the integrity of any of those structures will be compromised or not at the end of the day. The example is very much motivated from snooker, and it's an idealized problem for that, because in reality this object is a circular, cylindrical shape or conical shape rod or stick. So again, we are assuming the materials to be linear elastic. Ball has these kind of properties, while wall and the rod are assumed to have the similar properties as this one. Again, we have to plot stresses, and then we have to compare that if the stress in the wall reaches to the failure stress of the wall, which is 1 gigapascals, and we are assuming that the ball's strength is much higher than the wall itself. So ball can really not fail in any case. So let's jump into the real problem now. So again, the same approach video. So I already have, in the previous example, I have already shown you how to make different objects. So what I have done in this case, I have created a ball where I created a half circle and a line, and then I revolved it. I have created a wall which was a rectangular section which I extruded in the thickness direction, and then I created a analytical surface for the floor in this case, which is this one. And for that, what you can do, you can select, let's say, a 3D analytical rigid object. You create a line, and when you press done here, then you have to give a depth, and it will give you a rigid surface, which is basically this surface or floor in this case. So something like this, and I'm going to delete it for the time being. And this way I have created this part 4, which is the floor in this case, which is the bottom. So this floor will be there so that none of these things can move down. So we don't need to constrain the ball in any direction. It's just contact form. For this thing, again, we are assuming it to be 25 by 25 millimeter cross section rod with a length of 100 millimeters. So I will create a square cross section, and then I will extrude it to a depth of, or to a thickness of 100 millimeters. So that's what I'm going to do here. So once I have done that, I can create that, and this way I have created my rectangular object. Then I go to the properties. My properties are very much the same as before. I have created the ball properties, which are the elastic properties, and my wall is also elastic, and I'm using the same properties as that of the stick with the wall. So they have the same properties, while this is analytical rigid and it doesn't require any material properties at all. Once I have defined the material properties and assigned the sections, I can go and assemble the parts together. So I will go to assembly mode and instance the parts, and I can bring all the parts together and then rearrange them in such a way as required, as shown in this diagram here. So this ball is at a distance of 150 millimeters, while this stick can be at any distance. So I have tried to keep a minimum distance so that I don't have to solve it for a longer time. So again, I'm just solving it for 1 second in this case for a step in the step module, and it's a dynamic explicit step. As you can see, my nonlinear geometric options is on. I always do that just to avoid any kind of convergence issues if there is a large deformation. Okay, so for context, I'm using a general context. It's an excellent feature in Abaqus. You don't need to define any surfaces except for the rigid surfaces. For rigid surfaces, you will have to define which surface will be active during the contact detection algorithm. So that's what I have done here. So I go to the manager. You can see I have created one surface, and that is this surface, which is the top surface of this floor or the rigid surface, and you can see it's highlighted as red. So this is the only thing I have to do. If you don't define this, then when you run the job without this, it will give you an error that it cannot detect any surface for the rigid bodies. So again, you have to do that only for rigid bodies, even though if you are using general contact, which doesn't require any definition of surfaces. Now you go to the load module, and in this case we don't have any forces, but we are going to define displacements. So first thing is we are fixing the wall from the bottom as shown here in the problem. Then we are also fixing the rod in 2 direction and 3 direction while we are applying a velocity in the x direction as 100 millimeters per second as shown in here. And obviously we are not defining anything on the ball because ball has to move freely after the impact, so we're going to leave it free. While the last one is basically the rigid surface. Here I have created a reference point and I am fixing that reference point in all directions, so this means my floor will not move at all. Now to show you how the amplitude function really works, so this is amplitude 1 and you can create it from this button here, or you can go there into amplitude function and then you can create from here. Here I'm showing you how it works. So you see I have calculated that at a time period, at a time of 0.5 seconds, my stick will have traveled a distance of 50 millimeters. So I am keeping the velocity to be 1 times 100 up to this time, and after that it becomes 0. So this means this will not move at all after this time. So that's how I've defined the amplitude function for the velocity. So again, these are the small things which you have to do, but again you can use basic physics and mathematics to evaluate these kind of things in your problem. Once I have done that, now I have to mesh each component. I will do part by part. So again, you see net legal rigid surface doesn't require any meshing. Even if you try to mesh it, it will give you a warning or error that these kind of surfaces, rigid surface parts cannot be meshed. While for ball, again I have used a tet mesh, and for ball again I have used hex mesh. While for this component also I'm using a hex mesh by using this seeding and then meshing it as I've shown you in the previous example. Once I have done that, I will just run the simulation and I will create and run it. So I have already started the run, and it takes a long time, so I already started the run now, and it's been running for some time now. It's already approximately 900 seconds, so we are still going through it. And as soon as this finishes, I will show you how it goes. Even during this analysis run, you can still watch what's happening to your simulation. So I can go to the visualization module and I can see how far my simulation is being. So you can see the rectangular object has already struck or impacted the ball, and now ball is moving on its own towards the wall. So simulation has already started and things have started to move, but they are not finished yet, and it's only half of the time because it has to go up to a 1 second total time of 1 second. So yeah, so it keeps on going. Let's wait for it to finish. You can click on this and you can create some kind of animation, and you can see the animation as well, and so it can show you how it looks like, but still it's at an early stage. You can change the speed of the frames, you can set it to looping or just play once and then stop and then replay again by pressing this button here. So we are almost at the end now. As you can see, it has passed through almost 2000 seconds and it has completed almost now. So it took around 1807 seconds, which is a CPU time and not the actual time, because it's only how much time it wasn't with the processor, but reading writing can be more. So again, it might be slightly higher when you look at the overall time of the simulation. Okay, so let's see the result. Okay, so let's look at the results now. I have reopened the file because my simulation crashed, my Abaqus CAE crashed. So you can see now it has finished up to 1 second, and I can see that firstly it impacted the ball, and then ball started to travel and it hits the wall and then it rebounds back. So overall everything worked fine, and we can see what sort of stresses were generated during this time. Again, you need to be careful in such cases because it might be the case, since we have asked for a time for the output to be written at every 0.05 second, though, so the output might have been written after the impact rather than at the impact point. So again, this is again on your responsibility or analyst's responsibility to see at what point you are taking the output, because at exact impact point your stresses might be very high, while the output you written currently is just after the impact, so stresses might be lower than expected. Since it's an elastic problem, so it's basically depends on that. Okay, so you can see stresses were 0, then there was, as soon as the impact starts, you have stresses increasing, and then again starts to decrease since ball after the impact ball rebounds back, because everything is elastic. So you have elastic collision and then elastic rebound of the ball. So I hope this makes sense, but still stresses are very low, so I don't see any problem with any of these structures to be getting failed or something. So I hope this makes sense. It was a quick example. Again, I have a detailed tutorial on each of these examples, and it took me like more than an hour or so to do so. It might have been a very heavy lecture if I have put those detailed videos here, so I have tried to cut them down and bring the relevant parts into it. But if you want them, then get in touch or comment below, and I will definitely send you the videos or upload the videos, but they will not be without any, they will be without any comments. Okay, so this example is about drawing of a U-strip specimen, which is shown here. Again, it's an idealized geometry, so what we have to do is we have to construct something like this. In this case, it can be a plane strain problem, because you can see that strain in the thickness direction can be assumed to be 0 and maybe 0, so we are assuming it to be a plane strain problem. But you can try 3D as a challenge and see what you can do, and maybe you can upload your video below in the comment section. So again, I'm assuming the material to be linear elastic, which is this material which we want to form, and also for plastic part of the properties of the sheet, I am using these values which are given here to me. Okay, again, any arbitrary properties are given. I'm not saying it's any specific material right now. While these properties look similar to steel, while the density looks more similar to aluminum, so I'm just, it's an artificial material, just assume that. Okay, we are given the dimensions. I'm going to use those to make the drawing, and we are also given the dimensions of the sheet, which is a blank we're going to use as a starting point, and then we will form it to this kind of shape. Okay, so an important aspect is what I'm going to do is I'm going to create a rigid die, which is this part and also this part. I will also create a rigid punch here, like this part with these dimensions. I will arrange them together, and then I will put a sheet in between them, and I will form it with this speed. Okay, the most important thing is the blank holder here. I have eliminated that for the simplicity, to make it more simple, but blank holders are very important for sheet metal forming processes because they hold your sheet in place. What I will do, I will just create a boundary condition here, which is not realistic. If I use this blank holder, then what I can do as a designer, I can find out what sort of blank holder forces are required to keep this sheet in place when I push this punch down. So it's very important to have that, and you can just keep on pressing it maybe, and then see at what displacements or pressures you can really keep it at the place, which is the blank holder force, right? And then you can form it without any problem. So this could be there. Also, you can make these dies elastic if you're a die designer and you form a new material, and you can see if your die will sustain that amount of stresses or loading which is basically coming from this new material or sheet, whatever is there. Another thing is, if you want to really find out what sort of press will be required, because let's say you are working in a forming company and then you want to find out, I have 3 presses, which press I should use for this, then I can do a simple simulation here. I push the punch and I will find out what sort of pressures and forces I need, with which I need to move the punch downwards, right? So that force will tell me what capacity of press I really have to use to form this component successfully. So again, you can do a lot of exercises based on this. In this case, I'm going to make this die and this punch as rigid and this sheet as elastic plastic as given here. Okay, let's jump into this. I will first make the die, this line, and then I will make a fillet, and I will do the same on this side for this part. So I will make 1, 2, 3, and 4 parts in one by one. So in this case, I'm going with deformable 2D analytical rigid 2D planar wire case. So I'm going to make first part here. So it's 250 by 250 millimeter, I'm assuming it to be. So I will start with 0, 0, and then I'll go 250, 0, which is this point maybe. Then I will make a line downwards, hopefully, and it will be, or I'm going down from there. All right, so I'm making this one first. And it looks something like, and then I will select this fillet command from here, and I will create a fillet, and I am assuming the fillet to be most probably 50. millimeters. Yes, so I'm using a fillet radius to be 50. Again, this comes from the part geometry and also the spring back. Okay, then I will create the next one part of the die, which is this one. In this case I have to go again. Yeah, before going into that, I need to create, once I have created the part here, since it will be a rigid component, so I need to have a reference point, as I did for the last exercise. We need a reference point to apply all the boundary conditions. So I created the reference point by going into the tools and then reference point, and then select a point here. Then I will make the same thing for the other one or other part of the die, which is this part in this case, so 250 by 255, and then I will create a fillet of radius 50 millimeters. So I'm going from here to here, and then I will draw a horizontal line. Yeah, and then I will create a fillet of radius 50, which is this one or this one, wherever you like. It's a 50 millimeters, and then first entirety is this line, then the second entirety is this line, and it creates a fillet for me. Once I have done close and I have done everything here, then I will have to create a reference point, and I will create a reference point here for this part here, because it's also an rigid part. So that's what I have done here. So all the rigid components, you need to really define reference point, because then they are associated with that rigid part, and then you can define easily the boundary conditions. Now I am creating the top part, which is a punch, and again I'm given the dimensions. I will use the same filleting radius as for the bottom dies. So it's 0. I start from here, I went here, and then I'm going 200, 0, and then I will be going 200, 100 or something. That will give me this shape here. And then I will now create fillets between these two lines and these two intersecting lines. The radius is the same as before. And I have done that. Now I have to create a reference point. Best possibility would be I will have a reference point somewhere in the middle, but in this case it's easier for me to select it here or here, because I can directly click and select it. In any case, it's a rigid part, so there will be no issue with where you have, because everything will be the same if you have no rotation, since we are fixing all the rotations as well. So I have done that. Now I have to create a sheet. In this case I will create a 2D deformable shell, and I will create a sheet with the length of this and height of this. So I will create a rectangle. Use a rectangle command maybe. Yeah, so I will start from 0, 0, and then I will go, the next corner will be 700, 1.2. Now I have to define the material properties. As you can see, all the other things are rigid except for the sheet. I'm defining the sheet properties as given in the previous slide. Elastic properties are given to me, so I'm defining those, which is again 210 gigapascal and 0.3. I need to define the plastic properties. Again, these are coming from that table which was given in the previous slide, so I'm just copying it from there. Okay. I've defined that. Now what I will do, I will create a section which is a solid homogeneous with material 1 properties, and then I will assign it to this sheet. Here there is a question. I have defined the material properties, but I think I have missed something for you guys, and normally maybe it's now running into my blood after teaching for so long. I ask my students, so what mistake or what I'm missing now. If you know it, just comment it below, but I will tell you later on in the video. Just think in your mind that what I have missed in defining them during the definition of material properties, but I have missed something here. Okay, because it's an explicit dynamic analysis and I have missed something. Anyways, I have done that, and now I go to the assembly and I will again do the same. I will bring everything here, I can bring it here and it will be all jingle like that, meshed up. So, but if I press this auto offset, then it will be at certain distances from each other, and it might be easier than to arrange them. So that's what I'm doing here. And now I will bring this first here, and then I will translate it in this direction, and maybe then I can translate it here, and then this sheet here. So I will do it step by step, and you can follow the same steps in your case. Again, the distances are given to me, so I'm just using those here. So I will first bring it down to the same level as this one, and then I will move it in this direction. So I'll move, I can select this reference point here, and I can select this reference point here. Okay, and now I can move this to this distance which is around this. Again, you can play around with these as well and see what is the impact of this distance on this wall angles. So you can also play around with that if you want. Okay. And now I will bring this to the center of this point here, somewhere in the middle here. Again, there is no, I hope there is no similarity you find with the reality here, because these are just made up problems so that nobody gets in trouble, you know, because we do a lot of work from industries and other places. So I'm just trying to keep everything as general and as mixed up as possible. So now everything is very much arranged. Now I need to bring this here, so I will bring it somewhere here, the sheet itself, and then I will arrange to see. Now currently I'm trying to see what are the distances here. Okay, so that's 200 millimeters, as you can see here. I need to have 202, so again you can change that and see what happens. Okay, now I have to move this sheet here, and I have to arrange it here as shown here. And instead of blank holder, I will just fix this two edges, but not now. So I'll just select this point. So I will want to move this point to this point here. And once I click on and first point and then the second point, so I can see I have everything arranged in a very nice manner. The only thing is now I need to find out that everything is not going through each other, because we need to establish a context. So I need to move the punch up. The rest looks okay. So that's what I'm going to do now. So I'm going to move the punch up now slightly. As in the normal cases, you put the sheet, you put the blank holders, and you use the blank holders to fix your sheet, and then you press the punch downwards. Yeah. So I'm trying to move it up now. So I will move it to, let's say, 10 millimeters. If I'm happy or not, maybe not. So it's too much. It will take a long time. So I'm trying to bring it much nearer, and I used a 5 millimeter. Maybe I can use 1 or 2 millimeters as well. It's just to reduce the computational time, because during the travel we don't see any benefit until it touches the sheet. Okay, once I have done that, I can go to the mesh module and I can mesh parts. Okay, now what I do is I go to the step module and I create an explicit dynamic step, which is somewhere on the top here. Yeah, and then I run it for 1, and the geom is automatically on, everything is default, and I just press OK. Okay, so now all the default values have been used in this case. Next step is to define the interaction. So in this case, I will have to define the surfaces. I need to define an interaction. Since it's a 2D problem, so I cannot use the general contact formulation in this case, because it normally works for 3D geometries. So I will have to establish the context myself. So I have to define the contact between this surface and this surface, this surface and this surface, and also this surface and the top surface of the sheet. So that's what I'm doing now. So first thing is I'm defining the contact properties, which are again the hard contact and frictionless behavior. And I'm using surface to surface contact in Explicit, and then I will select surfaces one by one. So firstly, I'm defining the interaction between these two surfaces, the bottom surface of the sheet and the die on the right hand side. Okay, I selected the first surface and now I'm selecting the second surface. So let's try again. Surface to surface contact, first surface, yep, and then I will select the second surface. And since it's a rigid surface, so you need to tell which part of the surface it is. So you can see it's selecting the whole surface. First thing you need to ensure that, and it's on the magenta side, so I'm just selecting that. So now it knows there is an interaction. You can see there is an interaction created between these two. I will do the same between the bottom surface of the sheet and this die, or left part of the die. And again I will create this surface and that surface one by one. And again it's a magenta, so I will select magenta and then okay, so now it's created there. And now I will define the same for the top punch and the top surface of the sheet. And again in this case it's a yellow surface which will be in contact, yellow side, so I'm selecting the yellow side of it. Once I have done that, my interactions are all ready, and now I go to the load module and I will define the loading and boundary conditions. So what I will do, I will fix these two dies here, left and right part, in all directions, and rotation as well, and I will do the same for the other. And fixing in all directions again, so it doesn't move at all. And then I'll define the displacement boundary condition on the top side of this, and I will fix in horizontal direction and rotation, while I will apply a velocity of 30 millimeter. This should be 30, this is a typo here in vertical direction. So that's what I'm going to do now. So, and I'm applying a minus 30 because it's going to go in the negative direction. Okay, so once I have done that, I will go to the mesh module. I only need to mesh the sheet because the rest are all analytical rigid surfaces. So again I can choose a very fine mesh because I need more elements in thickness direction, so I'm using an element size of 0.3. and when I create the mesh I have 9332 elements, which is not that bad. I will go and I will start running. Here I have again made a mistake, and if you can find it, just keep it in your head and you can identify if I'm missing something or not based on this problem here. I have fixed this, I have fixed this, I have fixed in all direction except for the vertical direction. But do I need to apply something else? Let's see. I'll create a job and I will run it. So the first, I have made two mistakes now. One was during materials and second one is during boundary conditions. And let's see what these mistakes are and how Abaqus helps us to solve those. So I will submit it now. I think I have done everything correctly and I'm so happy, I'm confident, and then kaboom, there are errors. So you see it start and then you have error, and the first error you get is I didn't define the density. So as I told you, explicit dynamic analysis requires density because there is inertia term involved in the solution. So you need to define the density, and that's why we were provided density when the problem was specification was given to us. So this is the first thing we have sorted out, and now we again go back and run the simulation again. Okay, so I run the job again. So I have now got rid of that error and it's running, but let's see what happens. So I kept on running it, and it has reached to some point now. So if I now go back and try to see what's happening to my simulation, I can go back and press the results and I can see where my results are. So when I go to the results, I will find out that I forgot to define the boundary conditions for the sheet. So my sheet will, as soon as it starts to push down, this is free to move, so it will go up, right? So we don't want that we have a blank folder there for holding it. So what I'm going to do, instead of applying a blank folder, I'm going to fix these edges, both edges of the sheet from this side and this side, so that it doesn't move in vertical direction. And that's what I have done here. So I just fix 1 and 2 displacements in this, for this edge and also for the other edge, and then I will rerun the simulation. Again, the better approach is you should have a blank holder here, and that should be pressed with some kind of force so that your sheet is still there, but I can eliminate that, and I can also apply displacement boundary conditions here. Okay, once I have done that, now I will submit again, and I will rerun the simulation, and I will start monitoring now. So you see, now it has gone through very well. So I have killed the job because I already know that it has already gone through somewhere here. I don't want to run it for the whole duration. So once I have done that, I can create a deformable shape, and you can see it has nicely deformed around this area, and it forms very well. The contact works really fine, very well, and everything is working perfectly, so as we know. So again, what you see here is you basically, again, you can play around with the stuff, and you can remove the stuff and see what sort of stresses and strains are there in your sheet, and if it's gonna fail or not. But in reality, as I told you, what you can do, you can make these dies as elastic, punch as elastic, and if you have a new material which is very hard, then you can see then check the integrity of these dies. You can also find out the blank holder forces by doing this exercise. Also, you can also estimate the capacity of the punch press which is required to form this kind of material. So you can do that. Also, another important thing is, since it's formed, now if I move it back, in reality you have an elastic spring back, so it will not stay at there, but there is a kind of a spring back which will try to move the structure back slightly up. So you won't get the actual geometry, but it will be deviated from the actual geometry. So in reality, when you are designing the process, you have to really compensate for that elastic spring back, and maybe you need to form it more so that if it spring back, then it goes to the actual geometry after the spring back. So I hope you learned from this process, from this exercise, how to do a simulation for metal forming using explicit analysis. And yeah. This example is just for you to try on your own. It's a bending of a sheet, as you can see here, and then what you have to do is you have to bend the sheet by pulling this, pushing this die down while keeping this fixed, and once it bends, you have to remove it back, and you will see some elastic spring back here, so it will not be perfectly 90 degrees, and you have to find that spring back out, and maybe that will give you how much angle you have to compensate for during the bending itself. So it's a kind of a problem. I have a detailed tutorial on the similar case study on my channel, so have a look at that, which is more than 1 hour duration. So it's a very detailed one, and it was for one of my students. So have a look at that if you really want to try, or if you get stuck on something. Again, if you have any problems, you can again comment below, and I will definitely try to help you out in any way possible. Okay. Now next, and move to the next problem, and this problem is basically of a spherical ball object which drops on a steel floor under gravity. Again, my steel floor is like fixed from one end while it's free to move in the other direction. It's more like a cantilever case, but it's a 3D structure in this case, and we have a ball which is falling under gravity in this case. So all the properties are very much the same as previous examples with for ball and ball, and I think geometrical construction of the model itself will be the same. And let's jump into it, see how we can do it. So again, this is the sketch. We need to create a model like this one, so I will start with a standard Abaqus. Then I will first create the ball with a 3D deformable, and revolution as I did for before. So I'll create a half circle, a line, and then I will revolve for 360 degrees. So it's I call it sphere in this case. So it could be any spherical object which is dropping like a ball. So I'll create a half circle based on this. I'll draw a line to complete the sketch, and then I will press OK, and then it will ask me for the angle of revolution, and I will give a 360 degree there. So when I press done, it asks for me the angle, and I will revolve it by 360 degree to give me a complete sphere as I did before. So here's my sphere. I will do the same for the floor now. I will create a rectangle, and then I will extrude it in out of plane direction or orthogonal to this slide or screen in this case. So let me do that. Again, I call it a wall. I should call it a floor or something. Okay. Again, sometimes this gets stuck because I'm using a VPN connection. So, but it's just, you can't help it. Yeah. So I'll create a rectangle now, and then I will extrude it orthogonal to the screen. So it's 1500 millimeters times thickness, which is again given to me, and I've selected that and I've drawn that thing now. And then I extrude it to a depth of, say for example, in this case I'm using a depth of 500 millimeters, so it's half a meter, right? And now I will drop this, create a ball and wall assembly. First I will define the material properties, and again as before I have to define the density and the elastic properties for both ball and the floor itself. And now I'm defining the elastic properties of the sphere. And I will do the same for the floor now, which I am assuming to be made up of steel. Now I'll create sections, and then I will assign sections to the individual components. So I will call section 1 as floor, and I will associate the floor material properties with the section floor, and I will do the same for the case of sphere, and I will associate the sphere properties with the sphere section. Once I've done that, now I can assign those sections to individual components. So firstly I'm selecting the floor, and I will select this floor section which has floor material properties. Next I will go to the sphere and I will do the same for the sphere. Once I have done that, I go to the assembly and I will start assembling again. Again, the distance between the two can be as minimum as possible, but in this case we are limited because we are already given the displacement of a distance of 100 millimeters from the floor. So we have to move this ball now to a distance of 100 millimeters, and that's what I'm doing now. So I will translate it somewhere in the middle and then move it up in y direction. So I already know the dimensions, which was around 500 millimeters, so I have to bring it 750 on this side and then 250 on this side, and then move it up to a distance of 100 millimeters. So I will translate this from here to here, and you see it's there. Now I'll move it up, and so that the distance between the center of the sphere and the surface of the floor to be 100 millimeters. So I will do that now. So I will move this. I'm just trying to figure out how to define this vector to move it, and now I'm going to give it a value of 100 millimeters, and now I have 100 millimeters away from the surface. So once I have done that, now I can go to the next one step, and I can define a dynamic explicit step. So I can create a step. I will select dynamic explicit here, and I have my analgeom on again, and everything is just default, and I will press OK. Everything is just default. So for the time being, interactions, I have to create interaction properties, which is contact type. So I can basically create interaction properties by going to the manager, select contact, and then I can select the tangential behavior, which is frictionless. I can also specify some friction coefficient between the two surfaces, and for normal I'm using a hard contact formulation, which means that the pressure between the two surfaces will be based on the stiffnesses of the individual contacting objects. Again, you can look into Abaqus documentation for the formulation itself. For the timing, I'm just changing it to frictionless problem. So once I have defined this, again, since I am on the VDI, so sometimes resolutions don't match, so I'm trying to find a way to save or create the properties, since I cannot see the OK button. And now I'm using, since a 3D problem, so it's easier for me now. I don't need to create surfaces, although it's easier in this case, but I'm just using a general contact formulation so that Abaqus automatically detects if there is any contact made between any of the surfaces in the geometry. If there's a rigid body, again, remember you have to define the surface, at which surfaces will be active. Okay, I have defined that now. Now I go to the loads, and I have to fix my floor from one side, so that's what I'm going to do now. So what I'm going to do in this case is I'm gonna fix my block from this side. Yes, although it has to be on the other side, but I have done it this way, which is not correct. So in any case, I should have fixed it from this side, but again, you can change it and see what difference it's gonna make. I will have a large deflection here in this case. And the next is, I think, so I have fixed it from one end, and then I define the step, and I define the gravity here, so that this block, this floor basically, or this ball sphere basically falls with the acceleration due to gravity, and I am defining it. So again, it's in two directions, so I'm applying an acceleration due to gravity, two directions. So based on the density and amplitude, it can basically compute the values. I'm applying in this case as instantaneous. So as soon as the simulation starts, my structure will start to accelerate, which is acceleration due to gravity, and it will move in negative y direction. Okay, so all is set now. And now I'm trying to mesh each component. Again, the same issue. Either I should divide it into small parts or use it to very fine mesh. So what I'm going to do now is I'm going to use a tet mesh at the end of the day. So I'm going to go with a tet mesh now, and it should be easier than to mesh complicated objects. But then it's recommended when you have a tet mesh, try to use quadratic elements to avoid any volumetric locking and other stuff, which again I have spoke about it during my lectures, Introduction to FEM. So I'm trying to get that hex mesh for the floor now. It seems very fine, and you can see the elements are 19,000 and 37,500 for the floor. So it may take a very long time, so I'm trying to now reduce the mesh element sizes, element numbers, by increasing the size. So I have doubled it now, and let's see what happens to my element numbers if I mesh it again. And now it's only 5,000 elements, so it's better than before. And also in the thickness direction I have at least 3 or 4 elements, so that should be okay as a starting point. So now I just go to the job module and I run it after saving, obviously, because it's sometimes big jobs. When you start to submit, your CAE can crash and you don't know what's going to happen next. So it's better to save your job all the time. I normally don't prefer to use CAE to run the jobs, rather I use command prompt as I showed you in my other videos and lectures, because it uses a lot of resources as well. So I'm creating a job now. I'm in the job module, and I will just name it as object in spherical, just selecting a random name for that. Again, you see I haven't told you you can parallelize, you can use multiple processors, you can use multiple domains. So Abaqus can do 2 types of parallelization. One is processor based, the other one is domain based. So you can select loop or domain. When in domain decomposition, it basically decomposes your domain into 2 or 3 or 4 parts, and then it sends it to different processors and then assembles it together. While in the loop case, it basically your computational arrays are divided in simple terms, again in a layman's language. Okay. So in this case I clicked on this, and you can use 2 processors, but then my PC might struggle, so again you can avoid that. And this is the important thing for Explicit, always use double and full and accuracy, so that you don't do that. If you are not running it through CAE, then you don't have to select that from there, but you can use it in command prompt. So in this case, what I've done, I have written a right input file, and I will prefer to run it using a command prompt. So here I am on my command prompt, which is Abaqus command, and I already know my job file. So what I will do now, I will basically use the command which is Abaqus job equals to the name of the job, which is input file name, and then I will write double, so that double or double precision, it will now be incorporated here, so you don't need to select it there. And then I will run it in an interactive mode. And if I want to use multiple processors, I can say CPUs equals to 1 2 3 4, and also parallel equals to loop or domain, whatever. I think domain, right? I can also do data check, as in there was an option there in CAE by just typing data check here. In this case, I am running it completely in a full mode interactively, so it will give me all the outputs on the screen as you see here, which is very much the same as you see in the STA file or in the status tab when you monitor the job. So now it's running. What you see now is it's already finished. My job, all that is finished successfully, completed successfully. And now we go back to our CAE and see how it goes. It took around half an hour to complete this simple simulation, but it had a lot of solutions to do, because the ball has to drop and then has to move around freely. So a lot of things were required to be solved. So when you go to the results, you can already see, and the gravity has already an impact on the floor. It's already bending in the downward direction. I'm removing the mesh now so that I can see it more clearly if I can. Some people don't like it, I like it this way. So now under gravity, you see your beam is already bending slightly and the ball is traveling downwards, and at some point it will hit the wall and then it will rebound back. So it's like a bouncing of the ball. And since your floor is free from one end, so it's also tilting in one direction as you see this direction, so your ball will start to move and rebound back and go in this direction, which is natural in this kind of boundary conditions. Again, we could have fixed the floor from all directions, and then we can see more interesting effect that after how much time your ball settles down on the floor, for example. So again, you can play around with this. So now what I have done, I basically have run the job for 0.4 seconds, as you see here, and now I'm going to run it for 2 seconds in total. So I will give it more time to really move out of this transient state and see what happens at the end after some 2 seconds or so. So again, what I'm trying to do here is I'm also trying to change the output frequencies, which is at 20 intervals right now. So I can ask for more output, but then obviously my file size will be really big. So in this case, what I have done is I have asked for 100 outputs. So after I'm dividing the total time of 2 into 100 intervals, right? So it will write after every 0 point, let's say if it's 2 seconds, so 2 divided by 100 intervals times it's going to write. So again, I'm going to go back after writing the file and I will rerun it. Since everything finished fine, you can see it's my job size is, or ODB file size, which is the output database, is already 63 MB, so it might be further bigger, as it will have implication on the file sizes. But again, you can decide if you want to do again. What else you can do, you can remove some of the variables which are not needed in elastic analysis. So I'm checking which is not required or which will not be outputted. So I'm just removing those. In this case, there is no plasticity, so we can remove those. But again, they will not be written in any case, so but just to avoid anyway. I think so. You can play around with all these things to reduce the file sizes, and because file reading and writing will also takes time, and will increase the overall computational time of the job itself. So that's what I'm doing here. So I'm just removing any unnecessary variables which are not required, so that I can have the minimum. So I can only, you can see I am only asking for stresses, logarithmic strains, displacements, velocities, acceleration, reaction forces, and contact stresses. Okay, so now for history output, again they take a lot of memory as well. So in this case I'm reducing it because I'm not gonna check those. So I'm just asking it to write at 10 intervals rather than 100, and this will also reduce the overall file size for me. Okay, that's done. Everything is set now. So other than that, I'll just go and write the input file, or I can submit it directly from here. So in this case, I have submitted my job from here rather than going to the command prompt. So again, you can switch around and you can see which is good or which is bad. If your system is very busy with other stuff, heavy stuff, then you can run it in command prompt, then you will know that only one CPU is blocked, but CAE itself requires some extra resources as well, so that can also slow down your system. So in this case, I had nothing to do. It was a VDI system, so I just ran it on that machine using CAE. So now it's running. I will try to skip it. Yep. So you see now it has gone through all the steps and it has written 100 outputs, and it took around these many seconds, 8,977 seconds to finish, and everything was finished in time. So now I go to the results and see what happens after in 2 seconds time. So I will again go with the free edges or feature edges. So I'm still not displaying the meshes, and I've brought contours. So you see ball has disappeared, and now I need to see where the ball went. So it may have gone there. So now I start to go, once it falls, bounces back, and it keeps on bouncing because of the gravity and then the elastic repulsion or corrosion, and you can see stress waves generating in the floor because of that. And after, because there is a bending here, so there is an inclined plane here, so you can see this bounce will cause ball to go in this direction, and you can see after a certain amount of time which is this time your ball completely falls out of the floor. So again, it was just a test problem which has no reality in, but again you can think from your perspective that what happens, your kids are playing with the ball, or you see you yourself are playing with a ball, throwing the ball on the wall, you want to see what happens to the ball, then you can do that. Again, for the output, I have already had some videos on animation and everything, but in this case I'm trying to show you, you can basically create multiple views, multiple variables, or even you can use multiple files to have one-to-one comparison, create some interesting animations and images out of it. So I'm trying to here, in this case I'm creating different views, and then maybe see what else can be done. Okay, all is set, and now I can create an animation, but again you have to click each window. This is the problem with Abaqus, that you can't really do it in all together. So what you have to do, to click on each and bring them to animation mode. What you can do is you can go to the viewport and you can link them so they will all run in one step. Again, it's too fast, you can slow it down. So I have again a very nice video on that. You can link the viewports here, and when you link them, then they go with the exact same frames are shown in all the window, all the viewports. So again, whatever you do with one viewport, whether zooming in, zooming out, or pan, it will be reflected on the other, or affect the other view on the other side as well. And you can see how far the ball is going after 1.42 seconds, but it keeps on falling. There is nothing to stop it. Again, it's an unrealistic problem, but it gives you an idea of what is the potential of explicit dynamic in real life and what sort of problems you can solve. So again, look around yourself and see if you can simulate any specific problem. If you are using a mouse on a table, this could be a dynamic problem. You can also see you're pressing the button of the mouse with a finger. That's a dynamic problem. You can try that. What sort of stresses are there in your finger, for example? So again, think about different problems near to you and try to see how you can simulate that, and what will be the inputs required and how you can get those inputs. That's a very important thing. A lot of time as an analyst, you basically come across problems where you don't have all the data and you have to make a lot of assumptions. So again, and that's basically where your experience and sometimes your gut feeling or instincts come into play. So yeah, so play around with that. What else is there? I think I'm just trying to show you here how you can plot, but you can again play around with that. So in this case, I'm just going with one view, and that's pretty much it. So I hope this makes more sense now to you guys. And if you have any questions, again, you get back to me. This is how you can save interesting images at different instants of time, and these images again you can use in your PowerPoint, your presentation, your websites, or whatever. So you can see very high quality images. So Abaqus has very nice features to import and export images and videos and everything out of it. Even you can report the data as an XY, and then you can plot nice graphs in Abaqus in Excel as well, or MATLAB, whatever you like. Okay, so I hope this video helped you understand how to construct explicit dynamic analysis related problems, and how to set up the model, how to post-process the data, what assumptions you really have to make, what are the inputs required, what mistakes you can make as an analyst, and how Abaqus really helps you in rectifying those in many cases. So I went through some, I deliberately made some mistakes, and definitely you saw that Abaqus told us that okay, you need to define density, you need to define you need to see the boundary conditions because your sheet is moving freely, for example. So this kind of stuff. So as a concluding remarks, in this short course I gave you an introduction to Abaqus CAE environment. I also gave you an idea, or I tried my best to teach you how to perform static and dynamic analysis using Abaqus. During this whole exercise where I brought some examples, I try to give you tips and tricks for not only for meshing, but how to assume things, how to define boundary conditions and loadings, etc. Also creating geometries and also post-processing the results. Again, I have separate videos for those, so have a look at those if you're interested. Additional examples which I provided were just to give you a hands-on experience, so you can again modify those examples on your own and bring it on a more realistic grounds and then see if you can simulate similar stuff, or you can see around you where when you're sitting on a computer using a mobile, what your hand does to the mobile, pressing a button, can you simulate that? So that's basically what you can do. So hope you guys have learned something from it. If you need any more help on this, then please let me know in the comments below, and I will definitely come back with a solution to that, or I will try my best to help you out in that anyways. So thank you again and good luck.